So today we're going to focus on this field compaction. Specifically, we're going to go over compaction equipment, specification for field compaction, and also how do we determine the in situ or field unit weight. Okay. And the first one I want to go over is field compaction equipment. So for field compaction, it depends on what type of soil you are compacting, or you want to use different types of equipment. In general, okay, so field compaction. So in general, for cohesive soil, like clayey soil, okay, so you want to use a machine with relatively high impact pressure or impact force. And that's for clayey soil. And if you're dealing with granular soil, or cohesionless soil, and it is most effective to use shaking or vibratory actions to compact cohesionless soil. Vibratory actions. And these are most effective in compacting cohesionless or granular soils. And listed on this slide are 4 common types of rollers, and I'm going to go over each one. Basically, you have smooth-wheeled rollers, pneumatic, rubber-tired rollers, sheep's foot rollers, and vibratory rollers. And the first 3, they all apply relatively high impact pressures, so they are used for sandy and clayey soil. And the last one, the vibratory rollers, are mainly intended for granular soils. Okay, and so also I mentioned here, handheld vibrating plates can be used for compacting a small area. So let's go over these 4 types of rollers. The first one, this smooth wheel rollers. So this is intended for basically rolling subgrids and for finishing fields with sandy and clayey soils. And for smooth wheel rollers, the contact pressures are in the range of 310 to 380 kilonewton per meter square, or 45 to 55 pound per inch square inch. So that's the first smooth wheel rollers. And the second type, so this is called the pneumatic rubber tire rollers. And this is for compacting, again, sandy and clayey soils. And this type of roller has a much higher contact pressure, 600 to 700 kilonewton per meter square inch, or 85 to 100 pound per square inch. So that's the second type for sandy and clayey soil. But this gives you just a general range of the contact pressure. You'll see these apply different contact pressures. And then the next one, this is sheep's foot roller. And this one also for sandy and clayey soil, but the contact pressure, this one is the highest among the 3. So this is for mostly clayey soil, actually. And this one has the highest contact pressure among the first 3, in the range of 1,400 to 7,000 kilonewton per meter square. Okay. So these 3, as I mentioned, they apply relatively high contact pressure and intended for cohesive soil. The 4th common type, that's vibratory rollers. And for vibratory rollers, they can help compact granular soil or cohesionless soil. And this vibratory action is induced by basically off-center weights. So you see it on this graph, you have these off-center rotating weights, and they induce these vibratory actions, and most effective for granular soil. So these are the 4 common types of rollers. And then for field compaction, in terms of the procedure of field compaction, in the field, soil is compact in layers. So it's spread in layers. You have in situ soil and you have the feeding materials as well. And soil is spread in layers. And when spreading soil in layers, you use a predetermined amount of water to spread on each layer. So each layer is also called the lift of soil. And then after you apply that predetermined amount of water, and then you compact that soil layer with the desired roller. So depending on the soil type, you pick appropriate roller for that. And this picture, this shows basically the spraying of water in process. So you have this lift of soil, basically layer of soil, and you spread water basically to meet a specific moisture content requirement. And then in terms of what factors that will affect the field compaction effort. So there are a number of factors. The first one is the soil type, of course. And also moisture content. Moisture content. So in the previous lecture, we talked about factors affecting soil compaction in the lab. And you will see many of these factors actually, they are also here in the field compaction as well. So this soil type and moisture content affect field compaction. And then the thickness of the soil layer, thickness of lift. And the third factor is the intensity of pressure you applied. So that's affected basically by the roller type. So the intensity of pressure. And also related to this is the area over which the pressure is applied. So that's the area of the applied pressure. And the last one, the factor related to field compaction is the number of passes, so number of roller passes. So when you compact each layer of the soil, so you typically take a number of passes. So you drive the rollers back and forth for each layer. And the number of roller passes will definitely impact the unit weight, impact your field compaction effort. So I've shown this picture showing this basically the spraying of water during compaction. And this table here summarizes the different field materials for compaction. So you have soil types. And these symbols here, these are, remember that's from chapter 5, we talk about soil classification. So these are USCS soil symbols. And for each soil type, you have recommended roller for best results. So these rollers work for different soils. And then you have the maximum unit weight. So this is something you get from standard Proctor test. So you have this range of maximum dry unit weight, and then compaction characteristics. Okay. So that's field compaction equipment. So next thing I want to talk about is specifications. So basically, how do you tell if your field compaction is effective? Or how do you control your field compaction, basically? And there are two methods to basically specify field compaction. The first one is called method specifications. So one example is listed here. So basically, in the method specifications, you tell the contractor what methods to use, what equipment to use, and how many passes to take per layer. So example is here, spray moisture conditioned soil in loose lifts with a thickness of 12 inches. And then for each lift, you compact it with 6 roller passes. And also the roller type is specified. So that's called method specifications. And perhaps more common types of specification method is the second one. So this second one is called end product specification. So for end product specification, so basically you specify the end product. So I want relative compaction of 95%, and this is defined as the dry unit weight in situ. So that's the field dry unit weight after compaction over the D max. Okay. Times 100%. Okay. So that's the definition of relative compaction. Essentially, you're specifying the desired dry unit weight after compaction. So basically, I want how dense I want the soil to be after compaction. In this expression, let me use a different color. So the gamma D field, of course, that's the in situ field unit weight after compaction. And this gamma D max, this is basically the dry unit weight from standard or modified Proctor test. So that's what we discussed in the previous lecture. So in the lab, remember, you obtain that compaction curve, and from which you got that gamma D max and moisture content. And that gamma D max is used here to basically guide the field compaction effort. So I want the field gamma D to be a certain percentage of the maximum gamma D obtained from a Proctor test. Okay, so that's gamma relative density. And the other way to define relative density is to use the dry unit weight directly. That's for granular soil. Or I'm sorry, use relative density directly. So for granular soil. Instead of using R, I can use relative density dr to specify field compaction. So relative density. And this by definition, E max minus E, that's in situ or field. And this is from chapter 4 when we talk about soil structure. So relative density can be expressed using dry unit weight as well. So we can write this as gamma D field minus gamma D mean over gamma D max. Gamma D max over gamma D field. So here I want to point out, emphasize, this is could be confusing. There are two gamma D max on this slide. The left one in that relative compaction definition, that gamma D max is from standard Proctor test or modified Proctor test. But here, so these two gamma Ds, gamma D max, gamma D mean. So this is the gamma D corresponds, that corresponds to E mean, basically. And gamma D mean, so that's the gamma D corresponds to E max. Okay. So these two are not from standard Proctor test. These are from the ASTM test for E max and E mean. So you get E max and E mean, then you calculate the corresponding gamma D max, gamma D mean. Okay. So you have, so this could be confusing. Just make sure you understand the meaning of these gamma D max here. Again, left-hand side, that's gamma D max from Proctor tests. So that's used in defining this relative compaction R. And then on the right-hand side, in that relative density definition, these gamma D max and gamma D mean, these are dry unit weights corresponding to E mean and E max. So these are from a completely different sets of tests. So these tests are for E max and E mean. Okay, so don't confuse these two. And then one note here I added on this slide. So even though we're using gamma D max, gamma D as compaction specifications, the soil when compacted in the field is not dry. So the soil is compacted in moist conditions. So we're just using gamma D or this dry unit weight to specify compaction effort. So just keep that in mind. So that's the second method of specifications, end product specification.